Hello everyone. The next electrophilic substitution reaction of phenol is this. Phenol is going to react with phthalic anhydride in the presence of concentrated sulfuric acid, and we have to heat it little, due to which it is going to create one very important compound of a chemistry, phenolphthalein. It's an indicator which is used to distinguish between acidic and basic compounds. Topic is involved in 12th, JEE and NEET level. Let's check what that reaction is. Phthalic anhydride, the formula is this. We have to learn it. The benzene ring is connected with carbonyl groups, which are further connected with oxygen, which is working as a bridge between them. So this is phthalic anhydride. In this reaction, we are going to use white solid phthalic anhydride. Phthalic anhydride as a white solid substance, which is going to react with our very well known compound phenol. This is phenol. You know the nature of it. It's a colorless crystalline solid. In balanced chemical equation, two particles of phenol will be utilized. In the presence of colorless concentrated sulfuric acid, we are going to perform this reaction. When you will add these three chemicals and you will heat them, this compound will be generated. Check. This upper carbon you will keep as it is. This lower carbon you will connect with benzene rings of phenol on para positions like this. Like this. This one. Check. Carbon have to make 4 bonds. All the 4 bonds it is making. Initially, the 2 bonds were with oxygen. Now those 2 bonds will be joined on the para position of the phenolic ring like this. The compound which is generated here is known as phenolphthalein. In the form of colorless crystalline solid it will generate. Colorless crystalline solid. And what about this oxygen? As you know, here we have hydrogens. This H2O will be released out. Side product will be H2O. This is the reaction. Now up to 12th level, how we can learn this reaction? Check. Very easy to learn. This is phthalic anhydride. You need to know the nature of the atoms. This carbon is connected with oxygen. So electrons are going toward oxygen because oxygen is more electronegative than carbon. So this carbon is positively charged. This oxygen is negatively charged. Here we have phenols. Okay, the hydrogens which are present here obviously connected with carbon. It's a carbon. So carbon is more electronegative than hydrogen. So hydrogen electrons are going toward carbon. So hydrogen is carrying positive charge. Carbon is carrying negative charge. Positive charge, negative charge. So as you know, due to resonance, we know the resonance of phenol. Due to resonance of phenol, electrons are available on para position. So this carbon is highly negative, negative. Electrons are also available on ortho position, but ortho position will not be attacked by phthalic anhydride. Reason? Because look at the size of phthalic anhydride molecule, very big size. If it will attack on a ortho position, lot of steric hindrance problem will be there. OH and phthalic anhydride molecule will be very close, so steric hindrance will be there. That's why the compound will be minor. So to release out steric hindrance, the particle is going to attack on para position. That's it. O negative, H positive, H2O. Just release out H2O, and the 2 bonds of carbon. One, this is positive carbon, this is negative carbon. One carbon, one bond of carbon with this carbon, second bond of this carbon with this carbon. Rings will be joined and you will get your phenolphthalein. In this fashion, you can learn the reaction up to 12th level. It's not an actual mechanism. It's just a trick by which we can understand and we can keep in our mind. Okay, now let's go for the actual mechanism. Actual mechanism is also very easy. Let's start mechanism. You know, we are using sulfuric acid, H2SO4, and acids always provide us H positive particles. Your sulfuric acid will break in 2H positive and SO4 2 negative. These H positive particles obviously have a vacant orbital, means they are working like an electrophile. They want electron. So initially they attack on here phthalic anhydride particle. This is the first step. How? Check. Between carbon and oxygen, you know oxygen is more electronegative, carrying 2 lone pairs. That's why it is carrying a negative charge. So this electrophile which want electron will attack on oxygen for electrons. Due to which between carbon and oxygen obviously bond will break and pi electrons will shift toward oxygen. With the help of these pi electrons, this oxygen will make dative bond with this H positive. This is the role of acid. Due to which a carbocation will generate. This carbon as it is. You can use this carbon also. It's your choice. Between oxygen and carbon bond will break, only single bond will left because pi electrons will transfer completely toward oxygen, and these pi electron it is going to use to make dative bond with this hydrogen. Like this. When this hydrogen will receive 1 electron, so its positive charge will finish, and oxygen as it is, because it got 1 electron from carbon and it has delivered that electron to hydrogen side, and 1 electron as it is and this bond as it is. But carbon will be in the problem because carbon has lost 1 electron. This electron was of this carbon, it has lost it. So vacant orbital with positive charge. This will generate here. This is the role of acid. It will make carbocation in phthalic anhydride. Now this carbocation is also an electrophile. You can check. Yes, it is an electrophile because it wants electron. It have a shortage of electron. Now second step, who can provide electrons to it? Yes, the benzene ring of phenol. Let's check. This was the first step. Now the carbocation which is generated in phthalic anhydride, this one which is looking for the electron, who can provide electrons to it? Benzene ring of the phenol is a high source of electron. Which positions? Ortho and para. Reason? Resonance. Due to resonance, the electronic density is very, very high on ortho and para position, as you know. Many a time we have discussed. So it can attack on ortho position. This carbocation can attack on ortho position as well as on para position. But which position it will prefer? Para. Because if it will attack on ortho, steric hindrance will be there. Crowding. Molecules will be very, very close. So to release out that problem, it is attacking on this. Okay. Vacant orbital it want to make bond with this carbon, but for bond formation 2 electrons are required. In its orbital electrons are not present, so the responsibility of providing electron will be of this carbon. How? This carbon will bring pi electrons here. With the help of these pi electrons, it will make dative bond with this carbon. So the next condition generated will be this. Okay, this benzene ring I am making like this. Connected with OH, and fourth bond, the dative bond, it is going to make with para position of phenol. Like this. Now please watch. I have inverted this ring, so don't get confused please. here vacant orbital will come. This carbon who has lost its electron, this electron was of this carbon, and this electron has gone toward this carbon, here it is. And this electron, this carbon will keep with itself like this. So because this carbon is losing its electrons, so positive charge with vacant orbital will be generated here. What about this carbon? Obviously its positive charge will finish because positive charge was due to shortage of one electron. After making dative bond, it is getting that electron back. So its vacant orbital and positive charge will finish. But problem will arise for this carbon. Now this carbon will become carbocation, you can call it. Carbocation, or this ring rhenium ion. And this step is known as rate determining step or slow step. It is slow step. All the slow steps are known as rate determining step, RDS you can call it, rate determining step. Why they are slow step? Why it is a slow step? Because you can check during this step the benzene ring is becoming unstable. Right now it was aromatic. After this step it is becoming non-aromatic compound. It is losing its aromaticity. It is losing its stability. So that's why it is a slow step. And slow step will decide the speed of whole reaction. That's why we call them rate determining step. Okay. After this, what will happen? You know, many a time we have done it. This carbon has made this carbocation. So this carbon will make it stable back. How? By sacrificing its hydrogen. It will break bond from its hydrogen, will shift here, due to which from here H positive particle will release out. And between them bond will generate and this vacant orbital will be satisfied. So compound generated will be this. As it is, OH here, as it is, it will be connected with benzene ring. Now here double bond will generate, it is there, rest molecule, rest benzene ring as it is, phenolic ring as it is. What will be released out from here? H positive. H positive is released out from here. Now you can check, this is an electrophile and this was an electrophile. One electrophile has substituted another electrophile. That's why we are calling it electrophilic substitution reaction. The H positive ion electrophile was substituted by this carbocation, which was also an electrophile. Okay, what this H positive ion will do? It will attack on this oxygen for the lone pair because it will be in the close proximity of it. Here it is released and here oxygen is available with the lone pair. So directly this H positive will attack on this oxygen for electrons. What will happen next? Check. Now when this H positive will attack on this oxygen, the next molecule generated, let's quickly write it. With the help of this lone pair and the vacant orbital between them, dative bond will generate and only one lone pair will left. Hydrogen is already attached. Now due to this, oxygen will carry +1 charge, yes or no? Yes, because right now it is neutral. When it will make dative bond with this hydrogen, it will pass one electron completely toward hydrogen. So obviously it will get a positive charge and the positive charge of hydrogen will be finished because it got electron completely in its vacant orbital. So this oxygen will be in trouble now and rest molecule as it is, no change. One phenolic ring has been joined there, keep it as it is. Now what will happen? Oxygen is unstable, what it will do? It will break bond from carbon and will bring electrons back toward itself like this. Because it is more electronegative than carbon, so obviously when it will break bond for the stability, oxygen we know can't make three bonds. In 3 bonds always it is unstable. So third bond from carbon it will break and electrons obviously will transfer toward oxygen. Now when bond will break, what will release out? Let's release out it here. Oxygen will get 2 lone pairs, will become neutral and H2O. Water molecule will release out. But problem will generate for this carbon because it has lost one electron. Again vacant orbital with a positive charge will generate on it with the release of H2O. After this what will happen? It become again an electrophile, wants electron. Who can provide electron? Again a benzene ring of the phenol. Yes, the second benzene ring of the phenol now will be in the role. Where? Again, it wants electron. Who can provide electron? Benzene ring. Which position? Para position. Same mechanism. Attack. Let's join them. This is the condition now. One ring has already joined. Now this is going to attack the para position of phenol. Same. For bond formation, 2 electrons are required. It do not have electron. So the responsibility of electron providing will be of this carbon. How it will provide electrons? By bringing pi electrons toward itself, and it will use pi electrons to make dative bond with this carbon. That's it. Same pattern. When these pi electrons will make dative bond with this carbon, so the positive charge of carbon will finish because one electron will completely transfer toward this carbon. So its positive charge and vacant orbital will finish. So I have to twist this molecule like this. I have to write it. So please understand it. Now because this carbon has lost electron, this electron was of this carbon, it has lost it. So here vacant orbital with positive charge will generate. Hydrogen is already there. It will remain like this. Again, what will happen? This is a carbocation, arenium ion. How it will stabilize itself? This carbon will help it. How? By sacrificing its hydrogen. It will break bond from its hydrogen and will bring electrons here, and double bond will generate. And this hydrogen will release out as H positive. After this release, directly I am making a double bond here. This one. The compound which is generated here is known as phenolphthalein. That's it. In this fashion, phenolphthalein will be generated. Now what this H positive will do? It will repeat the whole cycle again. It will attack on the second molecule of phthalic anhydride. Same process, it will repeat again. And again carbocation will generate, and that carbocation will again attack on a phenolic ring, and the same pattern will be repeated. So concentrated sulfuric acid we have to use in very less amount, because once H positive has used, it will repeat the cycle again and again, and we will get phenolphthalein continuously. This is the mechanism of the reaction. That's it. This is the end of the video. Thank you very much for watching the video.